Hey, it has been some time since my last upload, but this is just the way things are going to be with this channel, at least till my routine is out. But anyway, this is just a little commentary on the latest developments that I'm sure everyone is familiar with by now. And but I don't want people to get the wrong idea that this is just for me to shit on the work of other people. So I want to make a little disclaimer before we continue. Uh, if you've been following the news and the media in general, you're probably familiar with the whole story, like how they pick these telescopes scattered all around the globe, and they synchronize them so they could use them as a Earth-sized telescope to get a high enough resolution to make an observation. And from there, the thing is just massive. It's like the whole fucking thing is like a saga. They collected terabytes, petabytes of data, starting like shitloads of hard drives, and they had to physically ship those drives to where the data would be analyzed. And then after all the fancy statistical modeling and the comparison with simulations, the end result of all this whole thing was like a shitty picture, like a fuzzy, a shitty picture. But also, we should recognize that this is also an amazing picture. And the reason it's amazing is because it shouldn't exist, but it does. And it does precisely because of the work of all those 200 plus scientists trying to piece together this puzzle by pushing both technological and scientific boundaries. And their achievement, which is a real achievement, will probably certainly produce new observations in the future, which will only further our knowledge of the cosmos. So, so it surely is a landmark moment for observational astronomy. So that's the story up to this point, and so far so good. As far as I'm concerned, everything is fine and dandy up to this point. But what I want to talk about is that there's this detail, this tiny little detail that seems to have gone over the heads of like everyone who's been talking about this lately.
On April 10th, 2019, the world saw, for the first time ever, visual confirmation that black holes actually exist. Technically, up until now, they only existed in theory.
This is the first ever image of a black hole. For now, the striking image of the black hole in M87 confirms beyond a shadow of a doubt that black holes do exist.
Last week, the Event Horizon Telescope project released the first ever image of a black hole.
Here it is, the moment you've all been waiting for. The first ever photo of a black hole.
By now I expect you've seen this picture probably many times. It's our first ever actual bona fide photo of a black hole. I mean, look at it. It's a freaking black hole. It's black, it's holy, it's everything we hoped it would be.
But the thing is here, they said, okay, so we think that general relativity is right, and we think there's a massive black hole in the middle of this galaxy, and we think that it's got a lot of this sort of radio emitting material around it. What would we expect to see if those things were the truth? And then they predicted this is what you ought to see, pretty much. And then you go out and take the picture, and there it is. And then so in some sense, that's the best proof there ever is when you actually predict something before you go and see it. And so I think this, in that sense, this probably is the best evidence there has ever been for a supermassive black hole in the middle of a galaxy.
Right, we have done something extraordinary. We've made the first picture of a black hole.
It's the best verification that we have that black holes aren't just theoretical scribblings on a blackboard, musings of theoretical physicists, but real entities roaming the universe.
We all understand from a mathematical point of view that black holes exist, but to actually see something is a very visceral experience.
Scientists have set out again. They will once more push the limits of astronomical knowledge. Their goal, to take a picture of a black hole. Something so ambitious that it seemed impossible. Until now.
I'm probably like the only person on the planet who cares about this shit. And precisely for that reason, it's probably gonna sound rather crackpotish of me to say that that picture is not nearly sufficient evidence to make the claim that what you see there, that black spot inside the orange donut, is in fact a black hole. And the reason this sounds so bad is because here there's a rather pernicious subtlety that's often not discussed in the mainstream science communication media. So the purpose of this is to sort of like fill that gap and expose this issue. To do this meaningfully, there's no other way around. We have to talk about general relativity. So I'll have to ask you to bear with me. But keep in mind though, that we're not gonna do anything formal here. I'm not gonna prove anything here. I'm not an expert in GR, but I can at least transmit to you what I've read about this subject in the literature. And this literature, if you so desire, is linked in the description for you to read up these materials and form your own conclusions on this matter. So what we need to get started here is we're talking about general relativity. We need the space-time patch. Where is the space-time patch? Well, here it is. Let's call it U. What else we're gonna need? Well, we are gonna need another space-time region. Let's call it B. And the complement of this, let's call it A. By the way, I should get this out of the way. Get this out of our way. This is not a space-time diagram. This is just a cartoon for visualization. And second, that no quantum theory here. Everything is classical, for the better or for the worst. And finally, that these limitations here are not just for shits and giggles. There's a physical purpose for them. The distinction between B and A is that region B has a non-vanishing energy momentum, while the stereo region has a vanishing one. So this stress energy momentum tensor is what people will generally refer to as mass or energy, but doesn't matter really. This is just the source of gravitation. Well, we need more. We're gonna need some conditions, some constraints, if you will, about this matter as well, whatever it is. So chiefly among those conditions that we want satisfied here is that this distribution here be spherically symmetrical, and that the gravity far away from it dies off, which, to put in the more technical terms, is the criterion of asymptotic flatness. Among other things, that's what we want here. And okay, this is just the setup of a problem. So what's the problem? The problem is, of course, solving the Einstein field equations. What are the Einstein field equations? Well, they are right here. Let's write them down. You could include here a cosmological constant, but never mind about that. It's not important. The important thing here is that if you're not familiar with this thing over here, well, this happens to be a system of 10 nonlinear second-order differential equations. So it's not like your typical Calculus 101 problem, or even Calculus 301. In absolute generality, solving these equations is super hyper fucking hard. So much that people can easily make careers of finding ways to solve them. But as it turns out, if our problem is nice enough with, enough symmetries and stuff, you can simplify and solve the problem. Exactly. And people have done that. The first person to do this was Carl Schwarzschild in 1915 in the trenches of World War I. And he came up with a solution for this problem. What's the solution for this problem? Right here. So it comes to no surprise that this is the Schwarzschild solution. And it describes this thing here, the metric field, which is the thing that we want to solve for in these equations, outside the distribution of matter, so in the region A. And well, this is like the basic solution, the simplest problem that you could ask for in this case. But as it turns out, you can be a little more general about it, because we want solutions for both the region B and the region A. So what we can tell about the metric generally? Well, about 10 years later, Birkhoff and independently a guy called Jepson proved a theorem about this. The theorem, if you read it carefully and you state it properly, it tells you basically that if you have these conditions of spherical symmetry and asymptotic flatness and whatnot, you have that the solution outside is just given by the Schwarzschild solution, and the solution inside here doesn't really matter. Roughly speaking, this is what the theorem tells you, that no matter what the metric looks like inside here, outside it must look like the Schwarzschild solution. And perhaps this is sounding a little too abstract for you, but this is nothing really new. Consider, for instance, the example of a charged sphere that is stationary. And you're only allowed to make experiments outside the sphere. You're only measuring the electric field of the sphere outside it. You're not touching it, you are not poking it in any way. So can you tell, for instance, whether this sphere is made of an insulator or of a conducting material? Well, that's about the idea here. And I think this, and I hope this can give you a glimpse of what I mean by an issue here with the ETH observation. By the way, I forgot to tell you what this RS over here is. That's right. Never mind what this M over here means. Like physically, you can think of as matter or something, but really, mathematically, it's just a parameter. It's just a thing that pops out when you solve the equations. But at this point, you might be wondering, well, when are black holes going to pop out here? Well, a black hole happens to be a model of what happens in this region over here. Generally, what happens in an interior region such as B. And for this case in particular, I could say, just like generations of others that came before me in a very hand-waving way, that one such solution would be the Schwarzschild solution. But that's not technically true, because such a solution will actually be the Hilbert-Roche solution. And even so, that would refer only to a so-called eternal or primordial black hole. We also have the possibility of black holes forming from stellar collapse, and these have been studied since the 30s, and they are way more complicated than this. But anyway, for our purposes here, it suffices to look at the solution and say, oh, at r equals 0, it kind of looks like a singularity, kind of behaves like a singularity, so that's what we are working with. And of course, we should notice that the r equal rs point is really just an apparent singularity, it's just an artifact of the coordinates, and this has been known for since a long time. Finally, I should mention a huge parenthesis here. The case that we've been discussing so far is a highly idealistic one, and as we all know it, nature doesn't usually care about idealism. So, a more realistic picture of what a clump of matter would do would be spinning around its axis and having very little electrical charge. And what would a solution for that be? The family of axis-symmetrical solutions is more varied here, but in particular we have one called the Kerr solution, which is like special because it includes black holes. And well, in this case, how could we modify these arguments, the previous arguments, to the case of the Kerr solution? Well, the things that we can say about such a solution in this case are less general than the BJ theorem, which is more strong, way more strong. But anyway, but still, we can still talk about certain unique features, and I believe one such result that is relevant here would be a theorem that was proven by Harper and Robinson in the 1970s, and it states that under certain conditions the Kerr metric is indeed unique. I believe that is relevant, especially and more so because what the EHT team was looking for specifically was for the solution, the Kerr metric. Indeed, they state explicitly on their papers that their no hypothesis was that the observations were described by the Kerr solution, and what they were measuring really were deviations from this metric, and what they found was that the Kerr metric is, there's certain limits, the observation is consistent with the car solution. That's what they found out at the end of the day. And they obviously were doing observations outside the clump of matter, outside of M87. So if the conditions that apply to the Carter-Robson theorem were valid here, and then I don't know if they are, but I suspect they are, then we would have the situation similar to the previous one. There's just this one solution that is the correct one for this case, assuming that general relativity is correct, of course. And in that case, anything that we could say about the interior here would become vacuous, just like in the previous case. It should be mentioned that the case that I'm making here is a moot one, because you can find all sorts of loopholes to bypass it. For instance, as I mentioned, these results for axisymmetric solutions are less general than the BJ theorem, so it's easier to find ways to violate those theorems. Another thing that you might raise is that there's an open question regarding whether you can, for instance, have a Kerr exterior solution attached to an interior non-Kerr solution arbitrarily. This is like an ongoing theoretical debate. And these are good points, these are valid points, and you can start a discussion on the comments. My point here, the takeaway, is that when you're talking about compact sources of gravity, you have to have these two conceptually distinct things in mind. You have the interior and you have the exterior. These two things, these two regions, are a priori independent of one another, unless there's some sort of mathematical relation that says this solution is uniquely tied to this solution. And why is that important? Well, if you are keeping to make measurements only of the exterior, just like the EHT team did, then in lieu of this one-to-one relationship, you cannot say for sure what's inside here, what's in the interior region. And as I mentioned, there is some room for doubt here, like for instance in the case of the Carter-Robson theorem. So the thing is, you can't really infer more than you have experimented for. And in this case here, what should be more appropriate to have told the press and everyone else? It should have been like, the result is that the exterior field of this compact object, the nucleus of the M87, is consistent with the Kerr solution. And the fact that there's a Kerr solution there is consistent with the idea that M87, the nucleus itself, is a black hole, is a Kerr black hole. But it's not conclusive. It's just like plausible within the empirical data. Finally, some concluding remarks here. I'm not going into the merit of why this communication has been so badly done. This would be like taking us to a whole other tangent. But I really want to say that this whole thing sucks. I want to bet you that come October late this year, chances are very, very high that the leaders of this project will get the Nobel for it. And like I mentioned in the beginning, it will be deservedly so, because in this case the deed does indeed correspond to the award. The problem is that the description of this award I'll bet you there's going to be something on the lines of for the discovery or the imaging of the first black hole or something like that. And that's it. That's the way it's going to go down the history books. And later on, there will be nothing really that we'll be able to do about it. I look at things like this and it makes me wonder, is this really the kind of example that we want to set to the future generation of scientists? That it's okay to embellish a little or a lot your actual results and your actual claims just so that they become more palatable to the population, they become more sexy to the public opinion. It is my personal conviction, and I hope that is also the case with you, the viewer, that the answer to this question should be a resounding no. Science, most often than not, is indeed a boring thing. But in spite of that, we should really stick with its methodologies. We should stick with it through thick and thin. Because otherwise we are not really doing science. We are doing Hollywood science. We are doing science entertainment. But anyway, this whole thing was really just my opinion on the matter. And I like to think it's an informed opinion. Even if it's ultimately all a bunch of bullshit. Because here's the thing, I'm not putting this up just to tell that I am right and everybody else is wrong. I'm presenting people with a viewpoint backed with logical argumentation and technical materials, which can then be conflated with the viewpoint that is being expounded by the mainstream media. And you, the viewer, is supposed to assess these two viewpoints, judge their merits, and see which one is more correct, which one is a more accurate description of what has been achieved. This kind of thing is really important to do because the accountability of science before the wider public really is bottlenecked by the quality of its communication. So if all you get is shoddy communication, you really won't be able to take a solid, strong, informed decision on scientific endeavor, which will then alienate you. And the best that you'll be able to achieve here is a sort of dogma, a sort of parroting technobabble and gobbledygook that others are telling without really understanding. And while you may not quite grasp all the technical details in science making, you should be able to grasp the purposes, the results that are behind it. Because science is really about knowing, it's not about obscuring. And if you have a result which purpose is made obscure to you, then it's either bad science or science being poorly done. The results should be clear, everybody should understand them. Well, this is really all that I had to say about this. So if you had the patience to sit through this whole thing, thank you. See you later. Bye, peace, and out.